All right, you guys. So today we're going to begin section 9.2. We started in section 9.1 getting into like the beginnings of hypothesis testing and a couple of the components. So now what we're going to do is we're going to actually go through an entire significance test or an entire hypothesis test. All right. I previewed this a little bit in class the other day, but with confidence intervals we used panic. And in confidence, hypothesis testing or significance testing, we're going to use phantoms, okay? The P is the same as in panic. It's your parameter of interest, your hypotheses we've been working on. Your A is still your assumptions. Here are our assumptions or our conditions. So similar to when we had confidence intervals, you still need to check to make sure it was randomly collected or a random experiment. Your 10% condition, you still need to make sure your population is at least 10 times your sample size. But your large counts, it's got to be n times p is greater than 10 and n times q is greater than 10. All right, here's the key, is it's not p hat or q hat. In intervals, it's p hat, q hat. In hypothesis testing or significance testing, it's just p and q. All right, and then as we go through, we will come back to these to check in. N still is the same, name of a test. T is your test statistic. This is your formula. All right, and up here we've got our formula. Now this is not on your formula card, but the basic idea is on your formula card. The basic idea is you have to have your statistic minus your parameter over the standard error of your statistic. And if you look at your formula card, this is under your standard error of your statistic for proportions. Your formula card gives you these p sub zeros. That's really the p from your hypotheses. Okay, so you will see that I often write it as p hat minus p over, and then I do p times q, that's a weird looking q, sorry, but p times q, right? Instead of 1 minus p, I'm just going to write q over n because I think it's a little simpler to look at. So that's usually what I use, and it's z equals. So I just rewrote this in a little bit of different notation. Okay, and then we're going to have O, obtain your p-value. That's when you're going to need to draw and shade your curve and find the area in your curve. Then you're going to need to make a decision like we were working on section 9.1 and then state your conclusion in context. So in panic, we ended with a C, right? C squared. It just doesn't make sense to be like phantom C. So that's why it's S, state your conclusion or summarize or however you want to look at it. So if we take a look at this first problem, all right, on shows like American Idol, contestants often wonder if there's an advantage to performing last. To investigate, researchers selected a random sample of 600 college students and showed each student the audition video of 12 different singers. For each student, the videos were shown in random order. So we would expect approximately 1/12 of the students to prefer the last singer they view, assuming the order didn't matter. In this study, 59 of the 600 students preferred the last singer they viewed. So do these data provide convincing evidence at the 5% significance level that there is an advantage to going last? So we need to go through phantoms. P is our parameter. We're gonna let P, the proportion, population proportion, equal the true proportion of students who prefer the last singer that performs. Okay, H, our hypotheses, null hypothesis. If you have P here, you have to have P here. If it's a proportion problem, it's a proportion problem the entire way. So we're going to let P equal the 1/12 because we would expect it to be 1/12 of the time you'd prefer the last singer. So if there's an advantage to going last, then our alternate hypothesis, if P is the proportion that like the last singer, then if there is an advantage, that means it's going to be greater than 1/12 or higher. Okay, our assumptions, random. Okay, now the random, not only was it a random sample of students, but we also had randomly change the order of the videos, which is helpful because maybe it was like legitimately the best person was last if they showed them in the same order every time, or the best person wasn't last. So by changing the order, it should randomly rotate, okay? Like the randomness should help with that. So we randomly changed the order of the videos and the students were randomly selected. So we had lots of randomness, which was great. Okay. When we do our large counts, that's when we're going to do n times p is at least 10, n times q is at least 10. So we're going to have 600 times 1/12 would be 50. Good. And then we're going to have 600 times 11/12, which is going to be 550, which is still good. Okay, we're going to have our 10% condition. Is our population at least 10 times our sample size? So we're going to work with, since they picked college students, then it would actually be all college students. If they didn't pick just college students and they just picked viewers, it would be the population of all viewers, okay? So it would be all college students. Are they at least 10 times? Oops, I didn't mean to put that. 10 times 600. Yes, of course, there's going to be at least 6,000 college students out there, right? It didn't say from one school, it just said college students. The name, I'm sorry, so we passed that test. The name for all proportion problems, just like with confidence intervals. Right now we only have one sample. These are going to be Z intervals for proportion. Okay, so we have a one sample Z interval for proportions. That's going to be the name. Just like with confidence intervals, our critical values always came with Z star, same idea. T, test statistic. Our test statistic, in order to get that, we've got to figure out what P hat is. P hat was 59 out of 600, which I get is 0.098. And then I'm going to look at the 1/12th, and the 1/12th I'm going to divide down, and that's going to be 0.083. Just because I'm a fan of typing in decimals into fractions instead of instead of fractions in fractions when I do my formula. So it goes Z equals P hat minus P over big square root P times Q. 1 minus P is 0.917 over N, 600. Okay, so it's numerator, big square root for the denominator, and you should be getting 1.33. And you know what? Now might be like the best time to pause, right? Like, what are we trying to accomplish? What we're trying to accomplish is we're trying to see, like, if there's truly no preference, then 8.3% of the time, the last person viewed is going to be the favorite. And in this sample, it was 9.8% of the time the last person was the best, the favorite as the best or preferred. So these are not the same number, right? This is 1.5% higher than what we thought was going to happen. So this is what we're trying to see is this gap between these numbers large enough to be statistically significant? Large enough to say, yeah, you know what, they're not the same? Or is it they're close enough that it could be the same, right? It could just be a fluke that it's a little higher, but it's not far enough to say, yeah, it's definitely different. Okay, that's what we're trying to figure out. So what we look at when we get our 1.33, now we need to go back to our hypotheses. We need to think, right? If our alternate hypothesis is P is greater than 1/12, then when we need to do O, which is obtain your p-value, we need to draw and shade our curve. Because if we have 1.33, that's a greater than, right? That's there. Our p-value is the area in that tail. What's the probability of being in this tail? All right. The probability of being here, we're going to get, so you're going to have p-value is equal to your norm CDF, right? It's 1.33 to infinity with 0 and 1. And we're going to get a p-value of 0.0918, which means there's if we go back to, because in section 9.1 we interpreted the p-value. So if we go back to this, there's a 9.18% chance that you can get a value this far apart from the truth by chance alone. It's a real good chance. 9% can happen, right? It's not like it's a 0.09% chance. It's a 9.18% chance. It can happen. So that's how we make that decision. Now, what happens is you don't have to be like, well, how close are they? We're going to let alpha guide the way for us. So you need to always show your comparison, okay? You need to show your p-value. You need to show the alpha you're using. I have 0.05 because it gave it to us here at the 5% significance level. If they didn't tell us that, you would still use 5%. That's like your automatic default of percents. And now you need to say what's their relationship. Your p-value is greater than alpha. If your p-value is greater than alpha, then the decision you make, remember this is M, make decision. P-value greater than alpha is do not reject the null hypothesis. Do not, do not, do not. Okay? And then you have to state your conclusion in the context. What does that mean? So if we don't reject the null, that means we can't say that we disagree with this, which means we can't support that. So there is not convincing evidence that there is an advantage to going last. You don't really actually want to put like that p is greater than 1/12. That doesn't explain the problem. Lots of students find it most helpful, and the AP encourages this, to put like there is no advantage. And then you can say this one is when there is an advantage. If you don't reject the null, that means we can't say there's an advantage. If we do reject the null, then there's convincing evidence that there is no advantage, which would then in turn imply there is an advantage. Okay? So all of these pieces is one problem. They're all required. All right, so if it says like, is there convincing evidence or perform a statistical test or something like that, all of this goes together as your work. So what I've done is I've gone through the next two problems and we kind of like broke them up a bit for you. All right, like I already pre-wrote them to kind of help with the speed. So according to the U.S. Census Bureau, the proportion of students in high school who have a part-time job is 0.25. An administrator of a local high school suspects that the proportion at her school of students who have a part-time job is less than the national figure. The administrator samples 200 students and finds that 39 of them have a part-time job. So I divided up here already, right? 39 out of 200 gives me 0.195. So 19.5% is her sample proportion, which yes, is less than 25%. Right? So she's saying she thinks it's less, okay? But we have to figure out now, is it small enough that it can definitely be concluded as less, or is it less but not less enough to be conclusive? All right? So as we go through, and if you want, if you got your pencil, you want to start trying these on your own, that's a great idea, okay? You first have to identify your parameter. Your parameter is let P equal the true proportion of students at that school who have a part-time job. Because remember, it's the administrator thinks her students have less. Your hypotheses should be P equals 0.25, P is less than 0.25. You always have to write HO, HA as well. Don't just like skip that, right? It matters which one's HO and which one's HA, which one's the null hypothesis, which one's the alternate hypothesis. Now we're gonna look at our I wrote this a little weird, set it up funny. So we've got our assumptions. Our random sample of 200 students from the school was chosen. 10%, the population of all high school students. We're gonna have to assume that it's a big school and they've got at least 2,000 students. We're gonna check N times P, N times Q. So we're gonna have 50 works, 150 works, we're good. our name. Right now, we only have one name for significance tests. So it's a one sample z-test for a proportion. I did my formula, right? P hat minus P over big square root P times Q over N. Remember, the P's are the one from your hypotheses. The P hat is the one from the sample. It's your sample proportion. All right. Then we're going to look over here, my p-value. When I get z equals negative 1.8, I come back to my alternate hypothesis, which is a less than, which means it's a left-tailed test. So I said my p-value is norm CDF, negative infinity to negative 1.8, 0, and 1, which then means I get 0.0359 for my p-value when you plug this in. And guys, type this in. Make sure you know how to do this. Like that, type this in and make sure you get this. And if you don't, you need to let me know and I can model it on the calculator in class. I can pull it up on the screen for you. Then you need to show your comparison, p-value compared to alpha, right? This time our p-value is less than alpha, which means you reject your null, right? So if you reject your null, then that means that this is what we're going to be able to talk about, right? So I wrote, we have convincing evidence that the true proportion of all students at this large school who have a part-time job, I forgot that part. That's the important part. Oops, sorry. Have a part-time job is less than 25%. All right, so if I were you, I would right now use a pencil, of course, so you can fix if you want, but try number 3 on your own. You're going to smush in your space. Sorry, I meant to tell you that before you started this. You're going to have to like budget your space if you've got really large bubbly handwriting. You can even use a separate sheet of paper if you want, whatever you want to do. All right, so number 3, if we start taking a look at number 3. All right, our proportion is let P equal the true proportion of all students at Sean's school who would say that they've never smoked a cigarette. I have null is P equals 0.68, alternate P doesn't equal 0.68, right? Because it's just saying, does the claim hold true? All right, so it's just saying, is it right or wrong? Right or wrong doesn't give us direction of higher or lower, or increase or decrease, so it's just equal, not equal. We've got our assumptions, all right? Sean randomly surveyed 150 students from his school, 10% condition, good. Large counts condition, good. Yes, I know this might be getting annoying that you're writing these every time. We got to get over it because this is here to stay, okay? It even gets bigger than this, but we'll build up to that. We've got our name, one sample z-test for proportions. You've got your formula, okay? So our formula, we've got if p hat equals 0.6, p was 0.68. I put this all in. I got my z-score to be negative 2.10. Now here's the trick, all right? If you have an equal, not equal, then we know that that means it's a two-tailed test. So what you need to remember to do, all right, and whatever notes you want to take to remind yourself, if it's a two-tailed test, you have to find the area for this tail and the area for this tail and add them together for your p-value. All right, so like when I did norm CDF, I got 0.0179, and then I just multiplied it by 2 because they're always going to be symmetrical. So whatever's this area is also this area, but you need to make sure you have the correct p-value. Okay, that's massively important. Two-tailed test, you have to get both tails because the area of it could be higher or it could be lower. So now we have 0.0358. We weren't given a confidence level or a significance level, so we're just going to use 0.05. So our p-value is less than alpha, which is 0.05, which is reject the null. Now, try to write your conclusion. What does it mean? If we reject the null, right? If we thought it was 0.68 and we're rejecting that, that means it's not 0.68. Please make a note. You can't go into assumptions, you can't go into reasons why, you can't go into it's higher or it's lower. If we just said it is or it isn't, then your conclusion just needs to be it is or it isn't. All right, so we have convincing evidence that the true proportion of all students at Sean's school who would say they've never smoked a cigarette differs from 0.68. Done. I'm not saying it's greater. Okay, even or less. Like, yes, this was less, But we weren't testing less, we were testing, is it equal or is it not equal? All right, and we can make that conclusion at the 5% significance level because alpha was equal to 0.05. So great job today on your notes. I hope you took nice, thorough ones. And then we will, of course, practice. See you soon.